The Planck length, which is 10 to the minus 35 meters, is there is a common lore or belief that the Planck length is the minimum or minimal length in nature, and that there is nothing or there is no meaning to a distance or a length below the Planck length. So in this video, I would like to tell you something that perhaps people don't know. The story according to string theory is much more interesting. Uh, According to string theory, the Planck length is where quantum effects, quantum gravity effects become important and cannot be neglected. This is where Einstein theory is not anymore reliable, and we should consider quantum corrections to it to modify the theory. However, according to string theory, the Planck length is not necessarily the minimum length. And in this video, I would like to explore this idea and to demonstrate it using some math. And so let's go and let's see what's really happening according to string theory. So, as I said, the Planck length is 10 to the minus 35 meters. It's a very, very small length. And usually we live in a macroscopic world where we measure lengths which are much larger. On general grounds, people anticipate that as we get closer to the Planck scale, quantum gravity will be more and more important. So if we write Einstein theory as square root of g r, that's the um, Einstein-Hilbert action. So r is the Ricci curvature, scalar curvature. On general grounds, we anticipate that there will be corrections to this action of the following schematic form: L Planck squared r squared plus dot dot dot. Namely, when the curvature is huge, we cannot neglect what we call quantum corrections, or in string theory it's so often called alpha prime corrections, but let me use this notation. I will use always L Planck as the Planck scale. Quantum gravity corrections. So actually string theory enables us to calculate reliably these corrections. And this is true on general grounds. It is anticipated, as I said, that as we approach small distances and curvatures become large, these sort of corrections become important. Okay, but that's not the full story. The full story is actually much more interesting. So string theory tells us a fascinating story. What string theory tells us is something quite amazing. Suppose that we have a universe, and the size of the universe, the radius of the universe, let's denote it by r. R is now not the curvature, it's the radius of the universe. Uh, so we have a universe of radius r. String theory tells us something quite interesting called T-duality. And T-duality is something remarkable. It's a duality between a universe of large radius r And it tells us that this universe that uh, is equivalent to a tiny universe. So a universe where with radius r, and r can be very, very large, is dual or have the same or another description in terms of a universe with a small r, such that r over the Planck length is the same or has a dual description in a universe with the Planck length over the radius of the universe. So, for example, suppose that L Planck we said is 10 to the minus 35 meters, and let's suppose that we have a universe with, I don't know, 10 to the 50 meters. I just invented a huge radius for the universe. Then we can describe the physics in this universe in terms of a dual universe, a different universe, where, let's say, r tilde is L Planck square divided by r, namely, what do we have here? 10 to the minus 70 meters divided by 10 to the 50 meters. So this is like, what do we have here? 10 to the minus 120 meters. So that's amazing. We can describe a universe with a huge radius with respect to the Planck scale using a different universe or different description actually of the same universe, but using uh, a dual universe with a radius of 10 to the minus 120 meters, a tiny radius. So it means that although at the Planck scale, 10 to the minus 35 meters, quantum gravity effects become important, we can have distances much smaller than the Planck scale. And the physics of that radius or this length is again classical. So we have something kind of interesting. This is length or distance. So at L Planck, we have quantum gravity or quantum gravity effects are important. But at larger distances or much larger distances, we have classical physics. So let's say around 1 meter. But also here at sub-Planck uh, scales, we have classical physics again. So at the Planck scale, quantum effects are important, but much below or much above, we have a classical description. Let me provide an intuitive explanation why what I wrote makes sense when we have a theory of strings. And string theory is the only reasonable theory of quantum gravity. It's the only consistent framework. So let's see. Suppose that we have a universe of radius r. Now, let's think about strings in such a universe. When we have a circle of radius r, strings can do two things in, in around this circle. they can either wrap the radius, and then we call these winding modes. So a string that wraps, let's say, n times the, this universe has length of n 2 pi r, and length is like mass. So because for the string it has a tension, so the tension times the length is the mass of the string. So the mass of such a string due to this winding mode is m, let's call it m winding, is n times r. Now, strings can do another thing, something that we are familiar with from, let's say, the guitar. When we have a string, let's say, attached to 2 points, it has these modes, etc. So, um, in addition, the energy of the string, or again, the mass of a string that vibrates, well, these are kind of vibration modes, is, let's, according to the mode of the string, is the energy is m divided by r. So m is the mode, first mode, second mode, etc. And the energy associated with each mode is the mode number m divided by the radius or the distance r. So in a universe of radius r, we have both the total energy of a string due to winding modes and due to uh, oscillation modes are the total energy is n times r plus m over r, and that's roughly, let me be now more precise, let me make everything dimensionless, and let me be more careful about units. So L Planck times m, this is a dimensionless quantity, is like, is m r over the Planck length plus m L Planck over r. So now we see the an intuitive explanation of T-duality. What we have is two modes of the string, and one of them goes like r over the Planck scale, and the other is Planck scale over r. And we have contributions from both. So what we see is that the total mass or energy of a string in dimensionless quantities, that's the left hand side, has two contributions. One is r over L Planck, and the other is L Planck over r. T-duality exchanges these two together with m and n. So what it really means is that strings that propagate in a universe of radius r have two contributions to their energy, and under T-duality we can exchange r over L Planck with L Planck over r, and at the same time exchange these excitation modes and winding modes. So in the dual description, where R over L Planck is becoming L Planck over R, we have the same contribution to the mass of the string, provided we exchange winding modes with excitation modes. And that's the intuitive explanation why um, strings in a universe of radius r and a universe of 1 over r are actually it's the same thing. That relates string theory propagating on a universe with a radius r to a universe with a radius 1 over r um, is similar to other dualities. So here we have something large, dual to, on the left hand side the radius is large, the right hand side the radius is small. Uh, Another duality which is familiar is electric, maybe more familiar to you, electric magnetic duality, where um, the field strength F is dual to star F with coupling goes to 1 over coupling. Perhaps it's more familiar with E, and B goes to minus B E. So electric magnetic duality maps um, one theory of electromagnetism to another theory of electromagnetism. But in one theory, the electric and magnetic fields couple with gauge coupling or with coupling G. In the other, it's 1 over G. So this is an example of weak strong duality. The non-abelian generalization, which is exists in both field theory and string theory, is called S-duality. Um, Another duality, which perhaps people from condensed matter are familiar with, is the duality in the 2D Ising model. And in the 2D Ising model, we have a duality between the low temperature and the high temperature phases of the theory. So if this is the temperature, we can map the high temperature theory to the low temperature. So this is really similar to T-duality. The last thing I would like to do is to present a proof of T-duality. I would like to show a derivation. Now, this is an advanced thing. It requires some string theory, knowledge in string theory, in field theory. So let's see. So the idea is that suppose that we have a circle of radius r, then we are talking about, if we include t, we are talking about a cylinder where this is a coordinate, the coordinate phi, and this is t. So this is our space-time. It is parameterized by phi and t. And the partition function of a string propagating on such space-time is d phi dt. This is the path integral. And what we have is r squared divided by L Planck squared d phi plus 1 over L Planck squared dt. Okay, so in string theory, phi and t are fields, and this is the partition function of a string propagating in such a universe. Now, let me add an auxiliary field. It's, as we shall see, it will do initially almost nothing, but this is a standard way of deriving a duality. So I'm just copying the previous action and adding to it a term d phi wedge d phi star. Sorry, not star. What I meant is tilde. Okay. Now, I didn't modify the theory. The reason is that if we write the equation motion for phi star, phi tilde, then we see that what we get is d star d phi is 0, and this is automatically just satisfied. So now the equation of motion for phi gives us a relation between phi and phi tilde, and this is more interesting. So the equation of motion for phi gives us the following relation: d phi tilde is r squared over L Planck square star d phi. So what it means is that phi tilde is dual to phi, and the prefactor is important. So let's substitute now, or let's carry out the integration over phi and get the partition function in terms of phi tilde. So in terms of phi tilde, we have the phi tilde dt e to the I, and then the first term is L Planck squared over R squared. This is achieved by substituting this relation, and then we have d phi tilde. This is L Planck squared divided by R squared, plus 1 over L Planck squared dt. So let's stare at this action. It's very similar to the first action. Time is still measured in units of L Planck, but this universe has radius r tilde squared over L Planck squared, which is L Planck squared over r squared. So what we see is that we have a dual description of the same theory, but this time in terms of r tilde, which is L Planck squared over r. So when r is very large, r tilde is very small, and vice versa. So that completes the derivation of T duality.